So welcome to back to a new term. In physics, we've been looking at a little bit of dynamics. We've done the work on the units, on dimensions, estimations. We've completed quite a bit of practical work, and there will be some practical work to do this week as well. But for today, I'm going to be teaching you about projectiles. I'm going to be using a slideshow I've managed to download from the internet and adapted for us, which will help guide you through this. So our learning objective really today is to make sure that by the end of the lesson you can describe projectile motion and you can do some basic calculations on it. So what is projectile motion? Well, if you get a golfer and he hits the ball follows a path. A trajectory is the path the ball follows, and the ball is the projectile. So the projectile motion is literally the motion of the golf ball in this case, or the thing that's actually moving through the air. So the only force that we're really going to worry about for the most part is going to be gravity. The simple reason in most projectile situations, particularly in exams, we tend to ignore air resistance quite a bit. So we're looking at projectile motion. We're looking at the idea that we've got, that we can calculate how far this golf ball will go if we know the angle at which the golfer is actually going to hit the ball at, and also the speed of the ball once the golfers hit it. That's the idea. It's useful in a lot of different things, including space travel. When you send a space probe to another planet, then it follows a trajectory which is governed mostly by gravity. So a projectile is an object in motion through space, and its path is called the trajectory. Okay, now the trajectory is curved because here the ball has two components of motion. It has a vertical component going upwards and a horizontal component going, in this case, from left to right. But what happens is its velocity, its vertical component of velocity, is going to be reducing as it moves until it gets to zero here. That'll have zero vertical velocity, and then will increase downwards as in the second part of its trajectory. So the path is actually called a parabola. It's not an arc, it's not part of a circle, it's a parabola. So the two forces that act on a freely moving projectile are air resistance and gravity, but we tend to ignore the effects of air resistance unless the situation means that it's significant. So for example, for a football, you would probably need to think about air resistance, particularly if it was going to be, if it's trajectory was quite a long distance. Okay, so the two things, because we ignore air resistance, then the air resistance will only really act horizontally. So we've got constant horizontal velocity because there are no horizontal forces on our projectile, but it's always accelerating downwards, even if the ball's moving upwards. Remember, a downwards acceleration when something's moving upwards is a deceleration or a negative acceleration. Okay, so because of that, horizontal motion is very easy to calculate because it's constant velocity, and the vertical motion is relatively easy because we're using our SUVAT equation, our constant acceleration equations, or SUVAT equations that we looked at before. So when is it a parabola? Well, let's have a look. So if we think about it, if we've got a golf ball being struck at 45 degrees, does it follow a parabolic trajectory? Well, yes, because the ball is very small and therefore has very little air resistance, so we can ignore it. So it's only not a parabola when air resistance is significant. So for example, a feather thrown at 45 degrees upwards doesn't really follow a parabolic trajectory because it's got a very large surface area, so air resistance is significant. So a paper airplane, for example, again, is thrown. Does it follow it? No, because the paper has a large surface area and the shape of the wings controls the flow of air, causing the plane to change direction. So we can't really ignore air resistance there. But if you have a netball thrown towards a net from 3 meters distance, although the netball's got a larger surface area, it's not really being thrown very far, so we can ignore air resistance. And in fact, in most cases, we ignore air resistance. A skydiver jumps out of a fast-moving plane. They don't follow a parabolic trajectory because their speed's very high, so air resistance becomes significant. But if you fire a cannonball then it will follow a parabolic trajectory, because although it still has a lot of air resistance, it's got a very large mass for its size, it's very dense, so we can actually ignore air resistance. That's the idea. So an object that's allowed to move freely through the air after initial force is called a projectile. The path of a moving object is called a trajectory. The downwards force on all objects moving through the air is caused by gravity. We don't really call it gravity, we call it weight, but it's caused by gravity. When we study projectile motion, it's useful to assume that air resistance is zero, because it makes the calculations a lot easier. And when this force is small enough to be ignored, the path of the projectile is parabolic. Okay, I'm assuming that you know what a parabola is from your maths lessons last term. A resultant force always causes acceleration in the direction. A resultant force always causes an acceleration in a direction I'm not too sure about this one. Was it parallel? Yes, to itself, so in the same direction. Okay, not a very clear question, that one. So an example of parabolic motion is to imagine you've got a cannon here firing a cannonball at a ship. Okay, as the cannon fires the cannonball, the 15 kilogram ball leaves the mouth. It's got a horizontal velocity of 150 meters per second. So if we think about it, the only force really acting, because it's a cannonball, so air resistance is fairly insignificant, we've only really got the weight of the ball actually acting downwards. So as it moves through the air, it's going to be accelerating downwards. So the vertical component of its velocity may be here minus 15, but the horizontal velocity hasn't changed. And with time, the vertical velocity will increase, but again, remember that the horizontal velocity doesn't change. So you can see that at any particular time, the horizontal velocity is constant, the red arrow here is constant, and but the vertical velocity is increasing over time because it's accelerating downwards due to gravity. That's because the only force really acting is the weight of the ball. So what we do when we're doing calculations on projectile motion is we tend to split the motion into vertical and horizontal components. So, for example, if you're dropping a crate full of supplies from a plane, if we ignore its air resistance, you know it will accelerate downwards, but its horizontal motion will be constant velocity. So what happens is, as the plane is traveling at constant velocity anyway, the crate also travels with the same constant horizontal velocity, but its vertical velocity increases as it falls. Okay? So you can see it's accelerating downwards. Well, here it says 10 meters per second squared. We know it's 9.81 really. So horizontal motion is constant horizontal velocity. Vertical motion is constant vertical acceleration. So the resultant velocity is just basically resolving the two vectors, the horizontal and vertical vectors. So the horizontal constant velocity is Vx, which is unchanged. It's not affected by gravity because gravity is at right angles. So force at right angles to motion will not affect that motion at right angles to it. And we know that it will be increasing vertical velocity due to gravity. The resultant is the resolution of those two vectors. So you use Pythagoras' theorem to get the resultant velocity. So if Vx is 300 miles per hour and Vy is 400 miles per hour, the package's resultant speed, well, all we do is we do a brief calculation. Okay, so bear with me. So if you've got and 300, you put the arrows end to end to resolve the vectors, just like I've shown you before.
I can't see it.
Sorry, there you go. Okay, you put the vectors end to end, like you did before, and the resultant is this one here, and you'd measure that. That would be 300 squared plus 400 squared, all square rooted for Pythagoras theorem, and that gives you 500, in this case, miles per hour. Okay, that's how you calculate it. It's fairly simple. It's not as bad as it's not as bad as it first seemed. So we could also, and you will tomorrow, do an experiment based on testing launch angle. The basic idea is if you're testing the relationship between the launch angle and the range of a projectile, obviously you need to change the angle. For a changing angle, we can measure the distance it actually travels. Okay, the projectile actually travels, and in order to do this, we need to make sure that we keep the speed of the ball when it's first hit by the golfer, in this case, the same. So if we think about it, we could already start to estimate which angle will give us the longest shot. Can anybody guess what it would be? Well, if we think about it, if it's 0, the ball would just go, if the launch angle was 0, the ball would just roll along the ground, so it wouldn't go very far. If it was 90 degrees, the ball would just go up and then back down again. So it must be somewhere in between. So logically, you would assume it'd be somewhere in between the two. And we can test it. So at 0 degrees, the ball just rolls along the ground as predicted. At 90 degrees, the ball just goes up and then straight back down again. And at other angles, the ball has a horizontal component of velocity and spends some time in the air, so it has a particular range. And as we test the different ranges, as we test the different angles, we get different ranges. You see that as we make it shallower, the range seems to be getting further and further, but only up to a certain point. As the angle becomes too shallow, the range starts to, the distance the ball travels starts to decrease. And we end up with a table of data. So if you plot that on a graph, you can see that peak, if we draw an imaginary line of best fit here, that peak would be round about 45 degrees. So when we're doing a mathematical problem based on projectile motion, we split the problem into two parts: the horizontal component of the velocity of the motion of the projectile, and the vertical component, and we use our CVAT equations. Okay, so let's have a look at an example. So let's have a trajectory. So we've got here a tower, and someone's cat keeps digging up the garden. So they want to try and stop the cat from digging up the garden. The best way to do it is to apparently shoot it. So to work out what speed this cannon has to fire a ball from horizontally from 8 meters up so that it hits the cat, you first of all have to work out how far it goes. Well, if we think about it, it's got to be traveling at 4 meters. It's got to be traveling 4 meters by the time it hits the ground. Okay, so what we need to do is work out, we know that speed is distance over time, so we've got to work out the time that has to be in the air for, so that we can work out the speed. The best way to do that is to just take the vertical component of the velocity of the projectile. So if we take that, we know that we're going to be 8 meters up. Okay, we know that it's got to travel 4 meters along. Okay, so we could work out the time taken, because the ball is the projectile starts off with a horizontal velocity. So if it's starting off with a horizontal only velocity, then the vertical component of the velocity, the initial one, is going to be 0. We know the acceleration is 9.81 meters per second. And we know the distance, the vertical distance, is 8 meters. So we could use the Suvat equations to work out the time. If we use Suvat, so the distance is ut plus a half a t squared. Well, that u is 0, so we can ignore that part of the equation. We can work out what t is, the time t. Well, t squared is 2 times the vertical distance, over, because that's divided by a half, over the acceleration. So that's going to be 2 times 8 over 9.81. So to get t, you just got to square root it. So you literally just use your calculator. 2 times 8 divided by 9.81 gives you 1.63. You then need to square root it. That's the bit that people miss out. So we end up with 1.277 seconds. Okay, so that gives you the time. Now, a lot of people, when they're doing these calculations in an exam, they're kind of panicking, and we try to submit that as the answer, but it's not the whole answer, because we want to work out what that horizontal velocity is. Okay, so the way we do that is we now take, so that's taking the vertical motion. Now we take the horizontal motion into account. We know the velocity, we want to work out the velocity, and that's going to be the horizontal distance over the time taken. We've just worked out the time taken. So the horizontal distance is 4 meters divided by 1.277, our time. And it's literally plugged into the calculator. 4 divided by 1.277, which gives you 3.13 meters per second. So roughly about 3.1 meters per second, maybe 3.2. So if we go back to our screen, we reckon it's going to be that one. Okay, and that's how we do it. So that is how you go about it. So let's do another example. So now we want to calculate how far this will travel. Okay, so it's 3 meters above the ground. We know it's being launched with a speed of 7.75 meters per second. We want to work out how far away from the tower Trevor was. So in order to do that, we have to take the vertical and horizontal motion into account. So if I stop my share for a brief moment, try and refocus my camera. My camera seems to have lost focus. I think it's because the room's warming up. So we know that it's 3 meters above the ground. And we want to work out that horizontal distance. And according to our question, it's traveling with a speed of 7.75 meters per second. Okay. Bear with me. Okay. So if it's traveling at 7.75 meters per second horizontally, we know that the initial vertical velocity is again 0. So we could work out how long it takes to fall. So we take vertical motion into account. Vertical distance is ut plus a half at squared. We know acceleration is 9.81 meters per second squared. So all you have to do then is know that that bit disappears again because there's no initial vertical velocity. So we want to work out the time. So t squared is 2 times the vertical distance over the acceleration. So to get the time, square root it. So that's 2 times 3 over 9.81, all square rooted. 2 times 3 divided by 9.81, square root it, and we end up with 0.78 seconds. Okay, that's our time. So now we take the horizontal motion into account. Horizontal motion, we know that the distance, horizontal distance, is going to be the horizontal velocity multiplied by time. So the horizontal velocity at the beginning of our question was 7.75 meters per second, multiplied by the time, which is 0.78 seconds, more or less. 7.75 times 0.78 gives you 6.045. So we call that 6.0 meters. Okay, so it should be 6 meters away. Let's see if that's actually worked, if we've got that right. And if we haven't, we can always unpick it. So here we are, 6.0 meters. Yep, spot on. Okay, so that's the simple way of doing it. Let's do another one more. So we want to work out, we know that the launcher's jammed on 3.34 meters per second. So we know the horizontal velocity is 3.34 meters per second. We know that the horizontal distance, the horizontal distance is 3.5 meters away, and we want to work out the vertical distance. Okay, so we want to work out which distance will enable the water balloon to hit the cat. Okay, so let's do that. So this time, I think we need to take the horizontal motion into account first. Okay, to work out the time. The time is the key bit, because the time the projectile spends in the air is going to be the same for both horizontal and vertical considerations. So the time is going to be the horizontal distance over the horizontal velocity. So the horizontal distance is 3.5. The horizontal velocity is 3.34. So 3.5 divided by 3.34 is going to give me 1.05 seconds. And then we take the vertical component into consideration now that we know the time. So we're going to use the vertical distance, which is what we want to work out, is equal to the horizontal initial velocity, vertical initial velocity times time, plus a half times a times t squared. So we know, again, this, as it's being launched horizontally, there's no initial vertical velocity, so we can ignore that. And we end up with a half a t squared. So it's a vertical motion only that we're really considering. So it's a half multiplied by 9.81 multiplied by 1.05 squared. So that's just a simple calculation. 0.5 is a half multiplied by 9.81 multiplied by 1.05 squared. That gives you 5.4 meters, allegedly. So if we go back to our puzzle, 5.4 meters, well, the closest one there is going to be the middle. There we go, job done. And that is roughly how you do those projectile calculations. So how do we observe projectile motion? Well, there are lots of different ways of doing it. One way to do it is to use a stroboscope. Now, I'm going to warn you that there will be some flashing images in this section of the recording. The stroboscope is basically a flashing light. So if you roll a ball off a flat surface, you place a dark screen behind it so that it shows up on very easily with a nice high contrast. And then you can use a flashing light and a long exposure on a camera to take pictures of the ball at various parts of its trajectory, so that you can then get the position, you can then measure the position of the ball at various points in time. Okay, and that gives you an image of the trajectory followed by this particular ball. Okay, so let's just check that we understand this. So, which word describes the shape of the path of a projectile on which the only force acting is gravity? So I'm going to ask Sheila, which one's the right answer there? Sheila, are you there?
Yeah, yes. Okay, I think it's D.
I think it's D, parabola, correct. Okay. Okay, Sadie, your turn. Apart from gravity, what's another force that can act sometimes on a projectile? Sadie.
Is it A?
Air resistance, well done, good. Okay, Sheila, so which of these would you describe as being a projectile?
I think is B or C. I don't
It's
know.
either B or C. D or C, or B or C?
B or C.
Well, is a pendulum that's swinging backwards and forwards? Is that really just something that's just moving under gravity?
No.
So it's probably C, isn't
I
it?
think C.
Okay.
Yes, exactly.
Okay.
Mm-hmm.
Okay, so Sadie, your turn. Which formula would you use to calculate the horizontal distance travelled by a projectile?
Is it A?
It's not A. Remember, the horizontal distance, the horizontal motion is constant velocity, isn't it? So the one that involves
I think it's B.
is B. Okay, good. Okay, let's move on. So which formula would you use to determine how long it would take for a ball to drop to reach a certain velocity? I'm going to ask Sheila.
A.
A, that's good. No, not quite.
No.
So we've got a constant velocity. Okay, so we've not got a constant velocity, so it's not B.
Yeah.
So we want to work out how long it takes, so we need time, so it's not C. So the answer is D. Okay? Simply because you only need to know the velocity, because you know that U, if it's being dropped, that U is 0. Whereas this one actually has some other aspects to it.
Oh yes, I understand. Yeah.
Okay. So a football is kicked with an initial horizontal velocity of 10 meters per second and takes 5 seconds to hit the ground. How far did it travel horizontally? I'm going to ask Sadie this one.
Is it true?
Sorry?
A. Is it?
Well, we've got a horizontal velocity of 10 meters per second. We know that horizontal motion is a constant velocity, okay? So it's a constant velocity of 10 meters per second, and it's in the air for 5 seconds. So it's traveling for 5 seconds. So how far would it travel after 5 seconds? Travels 10 meters every second, and there's 5 of them.
C then.
It's C, good. Okay. Okay, Sheila, what launch angle would you expect a projectile to travel the furthest? Can you remember from earlier on in the presentation?
Yes. C.
C is correct. Okay. Number 8, a ball is thrown horizontally from the roof with a velocity of 50 meters per second. So that's the horizontal component of velocity. It takes 15 seconds to hit the ground. What is the ball's final vertical velocity? So we're ignoring the horizontal velocity. We're taking just the vertical velocity. We can take acceleration to be 10 meters per second squared if you wish. So how do we calculate this one? So we know the acceleration. We know its initial vertical velocity is 0.
In this case, the initial velocity is 50, right?
Yeah, but we can ignore that at the moment because we're just looking at the vertical motion. So it's
Okay.
so it's basically it's accelerating at 10 meters per second squared for 15 seconds. Do you want a little help? Tell you what, I'll show you. So if the ball's traveling, so if we're just looking at just the vertical component, first of all, we know that it's fallen for 15 seconds. We know the acceleration it gives you is 10 meters per second squared. Okay, normally it's 9.81, but in this question they called it 10. Want to work out the time, want to work out the final velocity, final vertical velocity. Okay, VV. We know that UV is 0. So we look at our SUVAT equations and we know that acceleration is the change in velocity over the time taken. We want to work out that one. So we just rearrange it. So we know that that is 0. So it's just going to be acceleration times time. Okay. So the acceleration was 10 and the time was 15. So it's 150 meters per second is your actual time taken to fall. Okay. Okay, last question. A ball's thrown horizontally, again, exactly the same. We want to work out the final resultant speed. So how do we work this one out? Sadie? We know the final vertical velocity. So how do we work out the resultant speed?
Is it B?
It's not B because that's the vertical velocity. So we want to work out the two components. We need to add those two components together. So
This is like a Pythagoras, right?
this is sorry. This is like a what? Sorry.
Pythagoras.
Yeah, Pythagoras, isn't it? Yeah.
Yeah. Okay.
So we know it's traveling at 150 meters per second vertically, and it tells you in the question that its horizontal velocity is 50 meters per second. So just put the two arrows end to end. The resultant is that one. So if the resultant is that distance, the hypotenuse of the triangle. So it's 150 squared plus 50 squared equals the final velocity squared. So to get the final velocity, you've got to square root it. So you just plug that into your calculator. So it's 150 squared plus 50 squared equals, and then square root the answer, gives you 158.1. Okay, there's your final answer. So we look at that in our in our sort of options. It's 158 is the answer. Okay, so that is basically how it's basically the theme for this week is going to be projectiles. Now, I think from your responses, I think we've all pretty much got the right idea, but I think there's some more practice needed. I'm just going to switch to my camera. There's pretty much there's some more practice needed. So what we're going to do is we're going to add some more work to do. So we've just done our sort of our Zoom lesson, our first sort of 45 minutes Zoom lesson. And so what I'd like you to do then is to have a go on the Seneca assignment. So I've given you a link here on your Projectiles online lesson. I'd like to go on Seneca, have a go at the Seneca assignment, okay? And then I'd like you to then go back to the PowerPoint, which I've attached for you here. So if you've got a laptop with Microsoft Office, you can go through the PowerPoint slideshow again, or you can watch the video because I'm going to stop recording in a minute and put it on WeTransfer for you to download. Okay, so what I'd like you to do is to do that for the rest of this lesson. Okay, plenty of time, a little bit of reading up, and you can always also look it up on your study guide, which I gave you last term. Is that okay for you to do?
Yes.
Any questions?
No. It's
Okay.
okay.
Okay. So what we'll do is, if you get that done today, then I'll give you an online practical to do, a simulation, and also show you how to present data using Excel. It can often make life a lot easier, and then give you a chance to have a go at doing that practical. And what we'll do is we'll have a go at that practical, and then on the Thursday's lesson, I'll give you some revision time and some practice questions to have a go at on projectiles, so that we can be sure that you understand projectiles. Is that okay?
Yes.
Okay. Well, if there is anything, please email me or add a comment via the submission link on Show My Homework, and I'll get back to you as soon as I possibly can. Okay. In the meantime, enjoy doing the online lessons. I will try to be to have some Zoom time with every lesson, so that you have an opportunity to ask questions if you wish. Okay, take care, everyone.
Yes, thank you, Gary.
Okay, take care. Remember, if you've got any questions, just ask.
Yes.